In this class, we will discuss two methods of finding the optimal solution for uh, nonlinear, unconstrained, unconstrained, uh, unconstrained nonlinear optimization problems. Two methods. So the first method is steepest descent method. Steepest descent method, or it is famously known as Cauchy method. Cauchy's method. And yes, in this method you should know what do you mean by a gradient of a function. You should recall uh, from what you have studied in your beta classes. You should do it. You should recall the definition of gradient of a function f of x. So gradient of a function is denoted by del f of x, and it is a vector quantity, right? And that means it has both magnitude as well as direction, and our focus is on its direction. The direction of this gradient of a function is in such a way that it always direct towards, or it shows the the direction in which the function value or increases. That is, the gradient of function f of x, its direction will be in such a way that it always shows the increasing direction of this function f of x. For example, suppose your our earth, okay, and we have the air density, let it be uh, rho air we have, right? It is a scalar quantity like our f of x, and this function density of air is a function, and this density uh, air that constitutes our what our the surroundings. I mean, yes, the air density, when you go up towards the up in the up direction, that is towards space, then the density of air decreases. So if you apply the gradient of this density function rho air, that means del rho air, and it is a function of h, that is height. Okay, suppose it is a function of h, height, or we can say this density of air is a function of your three-dimensional space, that is x1, x2, and x3, or x, y, z coordinates, right? So this rho is a vector. Sorry, rho air is a function, scalar function x, where x is x1, x is vector x, that is x1, x2, x3, x3 transpose. Okay, so if you apply the gradient, what uh, it will have both the magnitude as well as direction, and the direction will be in such a way that it always uh, at any point, if you apply the gradient, then if you observe the gradient, then its direction will be in the towards the earth center of earth. That means the density of air increases towards surface of earth, right? So that means if you want the direction and in which the function is minimizing, you have to negotiate the gradient function direction. That means just you take the negative of this gradient. Then you will get the function, the direction at which the function got minimized. Okay, that is the basic concept. Yes, and this Cauchy's method is just the use of this negative of the gradient vector as a direction of minimization. Okay, and it is first made by Cauchy. And in this method, we start from an initial trial point x1 and iteratively move along the steepest descent directions until the optimum point is found. That is steepest descent direction. Okay, and the steepest descent method or the Cauchy's method can be summarized by the following steps. The steps are first start with an arbitrary initial point x1. Set the iteration number I is equal to 1. Then find the search direction Si. Find the search direction. The next step is to find the search direction Si. Find the search direction Si as Si is equal to minus del Fi, where F is already the same F that we have the objective function F of capital A. Okay, that is not going to change. So that's equal to minus del F of xi, and this xi I and this I are different. This I is from 1 to n, and this I is iteration number 1, iteration number I. Okay, this set as 1, and now we will determine the optimal step length. Determine the optimal step length denoted by lambda I star. Optimal step length. Okay, in the direction Si. The direction Si. That means you have to, in order to minimize the objective function, it is clear that you have to move in the negative direction of the gradient of a function, right? Now the next question is how far, how much step length you will move in that direction. Okay, and that is determined by this optimal step length. That means you will go in a magnitude of lambda I step length. You will move in that direction such that it will minimize the objective function, and it is known as the optimal step length lambda I star. And this finding this lambda I star, that we have already discussed in previous classes. So okay, so you go back there and refer it. Then the new point will be like this, that is xi plus 1 is equal to xi plus lambda I star si, and si is again vector. Okay, and that's equal to xi minus lambda I star del gradient fi. Why? Because this si is nothing but your minus of this gradient minus delta f of xi fy. Okay, then the next step is test the. Yes, so we got the new point. Now we are going to test the new point for optimality. Test the new point xi plus 1 for optimality of the objective function. Optimal. Then if xi plus 1 gives the optimum solution, stop the process. That means you will evaluate the objective function f of x at the new test point, that is xi plus 1, and if the objective function is got minimized, then we will stop the process. Otherwise we will go to the next step, that is step 5, and the step 5 is set the new iteration number, that is I is equal to I plus 1, and then we will go to the step 2. That means we will repeat the whole uh, all steps. Okay, so this method is very simplest of all. So, and also it gives better result, gives fast convergence also. And this method appear to be the best unconstrained minimization technique, since each one-dimensional search starts in the best direction. However, okay, yes, so this is our steepest descent method or cautious method. So we will explain this with an example. Minimize. So the example problem is minimize f of x1 x2 is equal to x1 minus x2 plus 2x1 square plus 2x1 x2 x1 x2 plus x2 square. And he has given the initial point, that is starting from the point x1 equal to 0 0. Okay, so the iteration step 1 is you set I equal to 1, that is iteration 1, and you have to find out the gradient del f. Okay, del f means you have to find out del f, that is equal to, that is nothing but set dou f by dou x1, dou f by dou x2. So this is an objective function in two variables x1 and x2. So dou f by dou x1 and dou f by dou x2 we will get. And if the objective function is in three variable x1, x2, x3, then dou f by dou x1, dou f by dou x2, and dou f by dou x3 you will get it. Right. Okay. So this is delta. Sorry, not delta. This gradient fi. Okay. So gradient f1 will be this, and gradient f2 will be and yes, that is dou f by dou x1, that will be equal to 1, that is partially derivating with respect to x1, that is 1 plus 4x1 plus 2x2, and here the partial derivation with respect to x2, then you will get minus 1 plus 2x1 plus 2x2, right? Yes. Then we have del f1, sorry, del f1 equal to del f of x1, that is equal to, we are evaluating, okay, we are evaluating the gradient of that function at the initial point x1 0 0, so that we will get 1 minus 1. Okay, so, and therefore we got the direction, therefore we got the direction at this point, initial point 0 0, we got the direction at which the function is actually increasing, because gradient is found. So but we have to minimize the objective function, so that means you have to find out the direction in which the objective function is minimizing. So that means that just the negative of this this del f1. So we got the direction s1 is equal to minus del f1, and that's equal to minus 1 1. So you should observe that all these are vectors, right? S1 is a vector, that means capital S1 I am talking about. Okay, capital S1 is a vector, minus 1 1. That means like your minus unit vector ax plus minus unit sorry plus unit vector ay, like this. Okay, this is a vector. So in the same way S1 is a vector, right? So yes, now to find x2 means your new uh, point, new trial point x2, we need to find the optimal step length lambda 1 star, right? Optimal step length. For this we have to consider the objective function f of x1 plus lambda 1 s1, and we have to find lambda 1 so that this function is got minimized, so that corresponding lambda 1 value will be lambda 1 star. So that means you will get it as f of f of, yes, I am substituting this lambda 1 s1, that means s1 is this vector. So this will be x1 minus, so x1 will be equal to, okay, that means this x1 plus lambda 1 s1 will be equal to, x1 is vector, x1 is 0 0, and plus lambda 1 is lambda 1 into s1 means minus 1 1, so that will be equal to minus lambda 1 and lambda 1. So this is what your x1 plus lambda 1 s1. So f of this, f of this vector, that means you substitute this vector, that means in place of x1 we have minus lambda 1, and in place of x2 we have lambda 1. So then you can you will be able to evaluate the objective function at this, and you will get it as f of minus lambda 1 lambda, that's equal to lambda 1 square minus 2 lambda 1. So this is again a quadratic function, so we can minimize this function. This looks like something like this or like this. Okay, like this, a quadratic function. So we will apply the Newton's method, so that slope is 0 and the second derivative is negative. These two we will apply. These two conditions we will apply. Okay, that means then you will get lambda. That means df by d lambda 1 equal to 0. We will equate, and d square f by d lambda 1 less than 0. This also we will find out this. Okay, so these two conditions satisfied, and then lambda 1 we will get it as lambda 1. Actually it is optimum step length lambda 1 star, that is equal to 1. You got. Now we will find out x2, the new trial point, new optimum solution point vector x2 equal to x1 plus lambda 1 star s1, that's equal to 0 0 plus 1 into 1 into minus 1 1, that's equal to minus 1 1. This is x2. Now now we will evaluate x2, right? We will evaluate x2, sorry, we will evaluate the objective function at x equal to x2, and we will find out whether the objective function is got minimized or not. Okay, and this del f2, and we will evaluate del f2 is equal to del f of x2, and that's equal to minus 1 minus 1 you will get, which is not equal to 0 0. That means this gradient of function, gradient of our objective function at the new uh, trial point, new optimum solution, is not equal to 0. That means it has got some magnitude as well as direction. That means the objective function is not minimized yet, right? If the objective function is got minimized at x2, then it should be 0 0, so that the magnitude and direction, all these are 0 0. That means there are no further direction for which the function is increasing or decreasing. Yes, then what we will do is we will go for the next iteration to find out the next optimum solution. That is, so that we will increase our iteration count I equal to 2. Okay, then we will we will repeat what we have done earlier. In the same step we will repeat here also. So this is our method, and you should go up to iteration 3, I equal to 3 we will go, and the convergence criteria is that means to what extent we have to repeat this procedure, these steps, is that is what we call it as convergence criteria. Convergence criteria is that the following criteria can be used to terminate the iterative process. That is, the first criteria is uh, the change in function value in two consecutive iteration is very small. That means you take f of xi plus 1, okay, minus f of xi you will take, divided by f of xi, and its magnitude, that is modulus of this, is less than or equal to epsilon 1, where epsilon 1 is a small positive value. Okay. So this is the first criteria. That means in this case you take x2 and x1 and you evaluate uh, f at x2 and f at x1, and you divide it with f at x1. Then if it is less than or equal to a positive, small, very small positive value, then you can stop it. Okay. Then the next criteria is the partial derivative. That means components of the gradient. That means partial derivatives means, in this case, dou f by dou x I x1 and dou f by dou x2. Or in general, you can say dou f by dou xi, and the magnitude of this less than or equal to epsilon 2, where I equal to 1, 2, 3, etc. n. I varies from 1 to n. So again, that means the gradient comes to 0, or close comes to a close value near comes to a value uh, very close to 0. Yes, and also another criteria you have to evaluate is that the third criteria is the change in the design vector in two consecutive iteration is small. The change in the design vector, that means the change in optimum solutions in two consecutive iterations is small. That means you got xi plus 1 and you got xi, then you take the difference and you take the modulus of this value, and if it is less than or equal to epsilon 3, another small value which is very close to 0, then also you so these are the you have to evaluate these three criteria. Okay, and if these three criteria are satisfying, then you can stop the iteration. Okay, now the next method is, we are going to the next method. Actually, in the previous problem we have just iterated for I equal to 1 and I equal to 2 only. Actually, they have in your textbook they have written, they have calculated for I equal to 2 and I equal to 3 up to I equal to 3, so you can practice that. Okay, now due to our time limitations, we are going to discuss the next topic, that is conjugate gradient method or Fletcher-Reeves method. Conjugate gradient method or Fletcher-Reeves method.